So this was the original motor. At this point, we kind of passed step one. The motor could work in the application based on what we saw at this point, but we needed a lot more detail. The motor was brought into our facility. This particular motor was brought in so that we could dig into it and look at it closely. So that's what we did. The motor was brought in. We dismantled. These are just quick pictures. We took it apart. I was looking at a lot of these details, getting measurements and details. This is an end view. Some of these are duplicate, and then the rotor. So the first thing that I noticed, and I don't know if you noticed in the picture, was that the rotor didn't have a shorting ring out here. What it had was a shorting ring down here, and it was unique. I've only seen this 2 times in 38 years of being in the industry. Yeah, my dad's been in it longer than I have. They had a strap that went from here that was like the bars were welded to this copper plate. That strap went down to here and then was welded to a smaller ID shorting ring that then was bolted to the face of the Spider. So a unique design. So not this style, this style. And then the stator. So what I quickly understood was that we really were looking at 2 things on this motor, the stator and the rotor. We weren't going to use their bearing system. I wasn't going to use the shaft-mounted exciter or any of the other details about that design. And we also understood that we had to use the original pedestal sleeve bearings that were in the original operation because of the shared bearing load, like I said, to those adjacent generators. So started making us think differently about what we had to do. So when the motor was in the shop, I'm going to go through these quickly. We took a bunch of data. We took data on the stator. We took data on the rotor, stator, rotor. We looked at the style of the Synchronous and how the coils were mounted, or the pole pieces were mounted to the Spider, in this case a dovetail with wedges. We looked at the cooling system. And then that was one piece of information. We had what we needed on that motor. Now we had to go on site and get a lot of details. Like back to this motor on site. We were able to have the customer shut it down for a few hours so we could go in and actually, or they pull off the covers and pull off the bearing tops and look at the sleeve bearings and get it to where we could actually physically measure and look at things. But what I quickly realized when we were doing this was that tape measures just aren't going to do it. You know, this shaft span, how many inches, Jim? I don't, it's on my 219, I think. So it spanned a long distance. You weren't going to get real accurate with a tape measure. So, but nevertheless, we studied it. We looked at the coupling design. We looked at all these details. That's the original. And if I happen upon something that you want to see again, just tell me, because I'm whipping through here because I have limited time. So the motor, the Synchronous motor, was a big diameter, and part of that diameter dips into the floor underneath. In the floor, or pit, I call it, you can see it coming down underneath. In that pit, they were actually feeding air in that pit that was bringing cooling air to all the DC generators in the motor in this whole tunnel. So it's kind of a cool application. Just looking at the leads coming out of the bottom of the motor, lightning arresters, surge suppression capacitors. But we had to, the reason I was studying all this, we had to be able to adapt to that. Our motor had to have 6 leads when it came out. We had to have the right configuration to be able to connect to their power system. Then we were looking at the way the motor was supported. There was an I-beam structure on the concrete wall on the edge of the pit, and it had gussets, which made sense, aligning with the biggest weight component of it, the stator. And it was clear we needed an accurate way to measure, like I said earlier. And we weren't going to do that from normal methods.